Hi, Michael Wolf, PGI compiler engineer. Here we're going to be talking about the deep copy problem and ways to solve that. So what's the deep copy problem? Deep copy occurs when you have a Fortran-derived type or an array of derived type, or a C or C++ struct or array of struct, where the struct members themselves or the derived type members have pointers to other dynamically allocated data. So by example, the problem occurs when you have an application that's going to look like the following. So here I've got my multi-core CPU with my system memory. And I'm allocating an array of structs. And each element of this struct has a pointer to some other data. And, oh, this can recurse. This might be an array. And this one, say, each of these elements might have a pointer to some other data. That's fine. Now I want to run this on a GPU. So over here, I have my GPU, highly parallel device, connected to a high bandwidth memory. I want to move this whole data structure over here. So I'm going to copy the base array. And then for each element of that array, copy its subarrays, its subordinate arrays. So for the first element, copy that array. The second element, copy that array. The third element, copy the third array, and recurse to copy the three things that it points to, and so on down the line. Now, when I copied the base array over there, one of the things I copied with it were the original pointers. So in fact, the pointers inside here are still pointing to host data. Now I need to do the attach. I need to take this element and make it point to the right data. So there's two pieces. There's three pieces: copying the base array, copying all the subarrays, and then doing all the attachments. That's the deep copy problem, and we're going to look at several ways to address this. So here I'm going to be looking at an artificial program. This is a program that allocates an array of derived type. So I have a garden array. This is to describe the gardens in my front and backyard. In each garden, I have an array of plants inside each garden. And inside the plant, I have some information about the plant, how many of them, what kind, what color, how tall, and so on. Later on, I will allocate my garden, and I'll fill the data and read the data from a file to populate the plants inside each garden. In my first example, I'm going to build and run this program using managed memory. Because I'm running on a Pascal GPU, I'm going to explicitly specify compute capability 6.0 and use the managed memory option. And if I look at my main program, it initializes the data structure, copies it to the device. With the managed memory option, I don't need to copy any data to the device. The managed memory device driver will copy the data automatically, and I don't need to copy the data back from the device either. Those routines are empty. None of that work is actually necessary. When I run the program, here it is showing the data that it read, and it's counting the number of plants of each type and the number of plants of each color and printing out that result. And what we can do to see whether what data transfers and what computation happened is set the PGI ACC notify option to 3. So this will print a line every time there's an explicit data transfer from host to device or back, and then we'll print another line for every compute kernel. And in the middle here, you'll see it transferred. These are two static arrays, so it transferred data for the static arrays, launched the kernel, transferred the data back for the two static arrays, but there's no other upload or download data for any of the dynamically allocated arrays because that's managed automatically by the NVIDIA CUDA device driver. But what if I wanted to manage that data manually, to explicitly determine what data gets copied over? I wanted to control it better or optimize it in some way. If you recall, the version of the program using managed memory, the routines to copy the data to the device and copy the data back to the host were empty. With manual deep copy, we're going to insert enter data directives to copy the original array, the base array, over to the device, and then a loop surrounding another set of enter data directives to copy each member array. So this copies the base array garden, and then for each garden element, I will copy over the dynamically allocated subarray plant. And similarly, when I skip down to the copying it back from the device, I will do a copy out of the plant members and then a copy out of the garden array. This is managing the data manually, and I'm going to build this with the PGI compilers and the T equals Tesla option without the managed sub option. It's going to get the same output as we would expect, but if I set the environment variable and watch the data transfers and the kernel launches explicitly, here we get to see the data upload. So this is the array descriptor for the garden array and the garden array itself. Then when I'm doing the sub member, here this is the first element has a member array that's 96 bytes long, and it also updates the pointer and descriptor for that member. And similarly, the second member has a shorter array, the third member has a longer array, the fourth member has another longer array, and so on. So each of these updates is going on while that's the explicit management of the data from the host to the device. Finally, it launches the kernel and then downloads the data as appropriate. Of course, it doesn't need to download the pointers or the descriptors. The manual deep copy feature is available in the PGI compilers now. You can use this in Fortran, C, or C++ to move structs or arrays of structs that have members that are dynamically allocated from the device to the host and the host to the device. The downside is you have to manually move the data for each member that you want moved, and for every update you have to manually update the data appropriately. So it's costly in terms of programming time. So in the next couple of videos, we'll be showing where PGI and where OpenACC is going to try to simplify the deep copy problem for you. Thanks for watching.